Alright guys, 3.4, velocity and other rates of change. And we've already connected position and velocity and acceleration yesterday with the CBR activity. But it says we have already seen that the instantaneous rate of change is the same as the slope of the tangent line, and thus the derivative at that point. Unless we use the phrase average rate of change, it's very important, we will assume that in calculus the phrase rate of change refers to the instantaneous rate of change or the derivative. The length of a rectangle is given by 2t plus 1, and its height is the square root of t, where t is time in seconds, and the dimensions are in centimeters. So let's just draw that right fast. We have a rectangle. We have its length is 2t plus 1. Its height is the square root of t. It says find the rate of change of the area. So the first thing we need to do is write an equation for the area. So the area, and it says with respect to time. Anytime you have with respect to time means of t, is going to be length times width. And I want to find the rate of change. Anytime you see rate of change, that just means the derivative, so a prime of t. Or sometimes you'll see that written as dA dt. And the d's mean, dA means change in area, and dt is change in time. So it's the change in the area with respect to time. So a prime of t, this is a product rule, so we would do 1 d2. Now I'm going to rewrite the square root of t as t to the 1/2. So d2 would be 1/2 t to the negative 1/2 plus 2 square root of t d1 times 2. And that's it. That's the area. It says find the rate of change with respect to time and indicate the units of measure. Now the units of measure would be the change in area. Now the area is in centimeters times centimeters, so it's really centimeters squared per second, because the change in area, the area is in centimeters squared, and the time is in seconds. Okay. Motion along a line. When a spring attached to a wall is stretched and then released, it moves back and forth. This motion can be described using functions involving sine and cosine, which we're not ready for just yet. However, motion along a line in other circumstances, either horizontal or vertical lines, can also be described using functions. Typically, we use a position function to describe the position s of an object after t seconds. Why they don't use p, I don't know, but they always use s, either s of t or x of t, to describe position. And this is very important. This is a big deal. It says the displacement of an object is the total change in position. And to find displacement, we just subtract. If we're trying to find from A, let's just say we're trying to find the displacement from A to B, we would do the position, S of B, minus S of A. The average velocity of the object is described as the total change in position, or the displacement, divided by the total change in time. It can be thought of as the slope of the line connecting 2 points of a position function. So the average velocity, and anytime you see average, it's going to be S of B minus S of A over B minus A. Average, 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 slope, every time. The instantaneous velocity of the object is the derivative of the position function. That's a big deal. So if you have position, let's just call it S of t. The derivative of position is velocity. The derivative of velocity is acceleration. So the velocity is the first derivative of position. The acceleration is the first derivative of velocity, or the second derivative of position. Let's see. Unless the term average velocity is used, we will assume velocity refers to instantaneous velocity. It is the slope of the tangent line to the position function. If it's a positive velocity, that indicates movement in the positive direction. If it's a negative velocity, it indicates movement in the negative direction. For example, if you were in your car, this car has no wheels. Here you are in your car, and you're facing, here's your windshield wipers. Your tail lights are back here. So this is the back of your car, and then your headlights are up there. Okay, so here you are in your car. Yes, it moves, except for it doesn't have wheels. Okay, I wonder if I put wheels on the car, would the wheels move with it? We're going to try. Wheels are gray. Let's see, what are the odds that my car will move in tandem? Is that the right word? Tandem? No one's here. No one can answer. Aw, of course it would do that. You knew it was going to do that, didn't you? Oh well. Car has no wheels. I hate it when that happens. Okay. Positive velocity. The car is moving forward in a positive direction. I'm going to hit a cat. I back up. Okay. That's negative velocity. If you are in reverse, you have negative velocity. If you're going backwards. If you're going forwards, positive velocity. Backwards, negative velocity. And back to the wheels. Velocity can have a sign. Speed is the absolute value of velocity. Thus, speed is always positive value, whereas velocity indicates direction. In other words, you could say, I'm backing up at a speed of 20 miles per hour, whereas if you said, I'm backing up with a velocity of negative 20 miles per hour. Velocity has a sign, speed does not. Acceleration is the rate of change in velocity, implying that when the acceleration is the derivative of velocity. Since it is the derivative of velocity, it is also the second derivative of position. I went over that. Okay, if I was standing in front of you, I would be pretending like I was a car and walking back and forth. But I'm not, so here I am. Pretend this is me. Okay, the speed or the velocity is your change in your position. My position's changing. It's the rate of change of position. Acceleration is the derivative of velocity. What that means is, if you push your accelerator down in your car, you go faster. So your acceleration has changed your speed. Thus, like, my speed changed because I pushed my accelerator down. I'm moving, I slow down. If I slow down, then I have changed my speed. So my acceleration changes my speed. If I let off the accelerator, my speed slows down, or my velocity slows down. If I push the accelerator down, my velocity speeds up. So acceleration is the derivative of velocity. And if you really wanted to know neat things, jerk is the derivative of acceleration, because if you push the accelerator faster, you might jerk. Like if you throw it to the floor, you jerk. It's called the third derivative of position. Alright, here's Bugs Bunny and Yosemite Sam again. Or is this the first time we've seen bugs? I think last time it was Willie Coyote, I think. Right? Wile-E. Bugs Bunny has been captured by Yosemite Sam and forced to walk the plank. Instead of waiting for Yosemite Sam to finish cutting the board from underneath him, Bugs finally decides just to jump. Bugs' position, S, is given by that formula, negative 16t squared plus 16t plus 320, where S is measured in feet and t is measured in seconds. It asks me, what is Bugs' displacement from t equals 1 to t equals 2? Well, you would do S, displacement is just S of 2 minus S of 1. Do you want me to type this in the calculator, or you want to just trust me? I'm going to type the first one in the calculator just to make sure we know what we're doing, and then from there on we're just going to trust me that I've already done it and to save time. Oh look, there's our CBR activity. Let me get out of that. Something neat. Let me show you something neat. Pull your calculator out. If we're going to be using the same formula over and over again, this is the coolest feature of this calculator. If you go to Menu, Actions, Define, I'm going to define S of t to be negative 16t squared plus 16t plus 320. And it tells me it's done. Now, I can actually do s of 2, s of 1, or if I wanted to, I could just go nuts and do s of 2 minus s of 1. Well, except for that, I didn't put parentheses. S of 1. Negative 32. So, his displacement, s of 2 minus s of 1, is negative 32, and that's feet. Because what have I done? When I find s of 2, I'm finding his position at 2 seconds, which was the what? 280, I don't remember. 288. His position at 2 seconds was 288 feet, and then it was 320 feet? Yes, at 1 second. So he fell 32 feet, because at 1 second he was 320, he was 320, and then he fell some more, and now he's at 288. So he fell 32 feet, so that's his displacement. The negative means that he fell. When will bugs hit the ground? Well, that's where we would set it equal to 0. And just a refresher on your calculator here, make sure we remember how to use it. We could add a calculator screen, and we could do s of x, and it'll take it from one screen to the other. Why did I use x? Because I can't use t. There it is. I want to know when it hits the ground, so I'm going to find my 0, and it's 5. I guess I could have used the quadratic formula or factored it, but it's just 5 seconds. We can do this on the calculator. That's a legitimate use of the calculator. There are 4 legal things you can do on your calculator. Find zeros, find a point of intersection, find derivative at a point, and do a definite integral, which we have not learned yet. What is Bugs's velocity at impact? Well, we need to find the velocity function. The velocity function is the derivative of position. So the derivative of velocity, if this is position, right there, 2 times negative 16 is negative 32t plus 16. So I would set that, what am I trying to do? What is Bugs' velocity at impact? Well, when does he impact? He impacts at 5 seconds, so you would fill in the 5. So it would be negative 32 times 5 plus 16, which is, you can trust me on this one, I checked myself before I started this video, negative 144 feet per second. Now, why is that negative? The velocity is negative because he, again, is falling down. Okay? What is Bugs' speed at impact? Well, his speed is the absolute value of velocity. Well, his velocity at impact is negative 144, so the speed would be the absolute value of negative 144. So he is traveling at 144 feet per second. His velocity is negative because he's falling down, but his speed has no sign. Speed is always the absolute value. Find Bugs' acceleration as a function of time. His acceleration is the derivative of velocity. Well, if the velocity is negative 32t plus 16, the acceleration is just going to be negative 32. And that's feet per second, because each time, to figure out the units, position is just feet. Velocity is the change in feet over the change in time, so it's feet per second. The acceleration is the velocity with respect to time, so it's feet per second squared if you take physics. So you can say feet per second squared. Suppose the graph below shows the, this goes with this. Suppose the graph below shows the velocity of a particle moving along the x-axis. So flip your paper. This graph is velocity. And this is Very important. This is a big deal. We're going to be doing tons and tons of these graphs. Velocity, remember, is the derivative of position. Now this is going to be a little tricky, okay? I'm going to go ahead and label this 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And just because this is so important, if there's any part of this lesson that does not make sense, I'm also going to post the link to Mr. Lecky's page. If you just didn't get me, watch him too to see if he can make more sense than I can. Alright, it says, which way does the particle move first? Well, it's moving downward first. Now, the velocity is going downward. So the velocity is negative. So since the velocity is negative, because this is the graph of velocity, because the velocity is negative, the particle is moving left. Because remember, if you're going backwards, then velocity, you have a negative velocity. So because this is left and right, left being backwards and right being forwards, he's moving left. B, when does the particle stop? Well, he stopped when his velocity is equal to 0, because that would mean that you don't have any speed, and that would mean you stop. So where is his velocity equal to 0? Well, his velocity is 0 at 3. At 0. At 0, at 3, at 7, and at 10. Okay. When does the particle change direction? The particle changes direction when the velocity changes sign. Because if you think about my car, here I am, just pretend I'm in a car. I'm in a car. Okay. As I'm going forward, I have a positive velocity. In order to turn around, I have to stop the car, throw it in reverse, and now I'm going backwards. I have a negative velocity. So what did I have to do? My velocity is positive, 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 then it's negative, negative, negative. So your velocity has to change sign when you change direction. So your velocity changes sign. Where does the velocity change sign? Well, it's negative, it's negative, it's negative, it's negative, it's negative, and right here at 7 it changes, now it's positive. So the velocity changes sign at t equals 7. When is the particle moving to the left? Well, the particle is moving to the left when the velocity is less than 0. Or, again, remember that what we're looking at is when it's below the x-axis. So it's below the x-axis from 0 all the way to 7, but at 3 it's actually 0. So from 0 to 3, from 3 to 7, it's below the x-axis. It's negative. I can't include 0, 3, and 7 because they're zeros. It's almost like you were doing a sine graph. If you were to make a sine graph of this, it would look like 3, 7, 10. It would be negative, negative, positive. No, that's all. Negative, negative, positive. Because you'd put your zeros on here, and you'd say 0, 3, 7, 10. That's what we're looking at right there. When is the particle moving right? Well, the particle is moving right when velocity is greater than 0. Velocity is greater than 0 from 7 to 10. Where is it? Above the x-axis. Where is it? Positive. From 7 to 10. And it just occurred to me that there's a good chance that this video is getting too long. So we're going to stop at the end of J. And we'll hold on to marginal cost for another video. Okay. When is the particle speeding up? Ooh, a tricky one. Here's a rule. The particle is speeding up when the velocity and acceleration and this stuff right here you're just going to have to memorize, have the same sign. Because think about me in the car, okay? When am I speeding up? When I'm moving forward and I'm pushing the accelerator down. When I let off the accelerator, okay, I'm moving forward. When I push the accelerator down, I'm going fast. When I let off the accelerator, I'm speeding up. So when I let off, I'm slowing down. When I let off the accelerator and I'm going forward, the acceleration is negative and my velocity is positive, so that means I'm slowing down. If I'm going backward, it don't really work with that. So just when they have the same sign. So, and remember that the acceleration on this graph is the slope of this graph. So, right now, let's just go through and in pink, let's do the acceleration. The acceleration has a negative slope. The acceleration is positive right here because it's a positive slope. It's negative, it's 0, it's positive, it's positive, it's positive, it's negative. Okay, because I'm just looking at the slopes. Alright, so where does acceleration and velocity have the same sign? Acceleration is in pink, velocity is in black. So velocity is negative, and right here it's negative. Acceleration and velocity are both negative here, and then here. On graphs like this, you could actually say that it's where it's moving away from the graph. So it's actually moving away at 0 to 1, U, 3 to 4, U, 7 to 9. When is the particle slowing down? Well, let's see. If the particle is speeding up when they have the same sign, it's going to be slowing down when velocity and acceleration have different signs. Okay? So, when would it be slowing down? At every place where it wasn't speeding up. Here, so between 1 and 3, between 5 and 7, and between 9 and 10. So, between 1 and 3, 5 and 7, and 9 and 10. When is the particle moving the fastest? Well, fastest indicates speed. So when does it have the highest speed? Speed is the absolute speed, is the absolute value of velocity. So, let me erase all this off the graph. I don't need all this stuff. Not my numbers. I need my numbers. Crap. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Where is it the farthest away is the question. If I were to do the absolute value of this graph and I was to do speed. Oh, look, I have to graph it in J. Let's go ahead and graph it now. Graph the particle's speed. What happens when you graph absolute value? What does it do? Remember, it takes everything below and flips it above. So it would look like brown. Really? I just chose brown. 1, 2, 3, 4. 1, 2, 3, 4. I didn't mean to choose brown. Nothing against brown. It's just not my favorite color. I typically choose brown. So this would be the absolute value of velocity, which is speed. And you can just copy that graph down onto the bottom, down here, graph the particle speed. The brown is the speed. So where is it the highest? Well, it's the highest between 4 and 5. You could have paused. Feel free to go back and pause or rewind. So it's the highest between 4 and 5. When is the particle moving at a constant speed? Well, that means there's no change in velocity. So that would again be between 4 and 5. Now graph the particle's acceleration. I'm going to do it up here and you're going to copy it down there. So, darn it, I erased my numbers again. Okay, the acceleration is the derivative of velocity. So that's the slope. So this is down 1 over 1. So I'm going to just put my little slopes on here. This is, what just happened? Did I erase all my numbers again? This is m is negative 1. Right here, m is up 1 over 2. M is 1 half. Down 1, 2, 3, 4 over 1. So m is negative 4. M is 0. Up 2 over 1, up 2 over 1, up 2 over 1. So m is 2. Up 1 over 1, m is 1. And down 3 over 1, m is negative 3. So if you remember that when you're graphing the derivative of straight lines, it's just you're saying from here to here. You're graphing a horizontal line at whatever your slope is. A half would be there. Whoops, it goes all the way, doesn't it? So right there. Negative 4, 1, 2, 3, 4 would be here. And then 0 here. 2. It's right there. 1 from here to here. Whoops. And negative 3, 1, 2, 3. So you would copy that graph down there, the acceleration graph. And remember, you need to have open circles because there's pointy places, so the derivative doesn't exist, so you can't close your circles in. Alright, that's it for today.